Today we'll be looking at concavity and points of inflection. So to begin, let's talk about concavity. Concavity describes the curve of the graph, and when testing for it, we need to make use of the second derivative. Remember, the second derivative is a derivative of the derivative. So for example here, given f at x equals 5x to the power of 4 plus 3x squared minus x plus 1, we want to find the first and second derivative. So we're first going to do our first derivative here of our f at x, and what we're going to get is 20x cubed plus 6x minus 1. Then if we take the second derivative of this, we're going to get 60x squared plus 6. We should all be pros now at taking our derivatives, our first and second. So we're going to look at 4 different situations here. First, we're going to look at when we have concave up and increasing. So we will have our graphs to look both of them to look like the following. The first two here, since they both are concave up and increasing. Here, our second derivative is going to be greater than 0. And again, this will also be our second derivative being greater than 0. Now, looking at concave down and decreasing for the next two, we have two functions. And here, is going to be the opposite of when looking at concave up. Our second derivative is going to be less than 0 in both cases. So let's talk about concave up and concave down. So the graph of the function, when it's concave up, is going to be above the tangent line at every point on the interval. Now, with concave down, the graph of the function is going to be below the tangent line at every point on the interval. So to sum that all up, f at x is concave up on the interval where f double prime of x is positive, because the slope is increasing on this interval. So at the critical point, x equals c, if f double prime of x is greater than 0, the critical point is a local minimum. Now, talking about when our function is concave down on that interval, where f double prime of x is negative, because the slope is decreasing on this interval. So at that critical point, x equals c, if f double prime of x is less than 0, the critical point is a local maximum. And when talking about our point of inflection, this occurs where the curve changes from concave down to concave up and vice versa. So to sum that up, this is when our f double prime of x changes from positive to negative, or vice versa. They occur when f double prime of x equals 0 or when f double prime of x is undefined. So now let's go ahead and look at some examples. So in example 1, we want to sketch a graph of y equals x cubed minus 3x squared minus 9x plus 10. So what we're going to do, our first step, we want to find the derivatives. And why I say derivatives, because you want to find both the first and second derivative. Okay, and we want to solve for our f prime of x is equal to 0 and f double prime of x is equal to 0. So let's go ahead and do our first derivative. So y prime is going to be equal to 3x squared minus 6x minus 9. Now we're going to set that equal to 0. And when I do that, I can factor out a 3 here, and I'll be left with x squared minus 2x minus 3. I can now factor two numbers that multiply to negative 3, add to negative 2, is going to be x minus 3 times x plus 1. So therefore I have x equals 3 and x equals negative 1. These here are your critical points. Alright, now we need to take our double derivative. So we get 6x minus 6. Now set this equal to 0. I can factor out a 6 and I'm left with x minus 1. So therefore we have x is equal to 1. So now using the fact that when we solved for our second derivative we got x equals 1, we're going to look at that in terms of our f double prime of x and talk about our function and talk about if it's concave up or down. So our second step is to do exactly what I just said. So we're going to look at our f double prime of x and then look at our function itself. And we're going to look at it at 1. And we're going to look at it on either side of 1. So on the left hand side and the right hand side. So on the left hand side, if you take a value, looking at your f double prime of x, so if I were to say take 0 and sub it in there, or you can take a value such as 0.9, which is very close to 1 but isn't, you're going to get a negative. And when my f double prime of x is negative, my function we know is going to be concave down. And then we look at, well, what about on the right hand side of 1? Well, if we take a value, let's say 1.1, I'm going to get that my f double prime of x is positive, and therefore I know it's going to be concave up. So x equals 1 is a point of inflection. So when f at 1, we can solve this and we get that our function will equal negative 1 at this point. Remember, we can find that by just subbing in 1 into our original equation. So now, looking at that, I know that my function is going to be concave down when x is less than 1. And I know my function will be concave up when x is greater than 1. So now we also need to look at our critical points. So remember our critical points we found here when we were looking at our first derivative. So looking at our critical points, at x equals negative 1, what happens here? Well, I know if when x is equal to negative 1, my function, the point that exists, is going to be negative 115. And since I know that my function is going to be concave down on the left-hand side of 1, I know that this will therefore give me a local max. And then looking at x equals 3, my point that exists would be 3, negative 17. If we look on the right-hand side of 1 here, remember, anytime that x is greater than 1, we know my function is going to be concave up. And since it's concave up when x is greater than 1, we know that the function is going to give us a local min value. So now using all this information, we're going to go ahead and graph this. So now let's go ahead and graph our points here. We know we have a point of inflection at 1, negative 1. So what I've done here, my x-axis it goes up by 1s, and my y-axis is actually increasing by 4s. So I have the point 1, -1 here. And I also know that I have a local max at -1, 15. And I have a local min at 3, -17. I also know, just by looking at my original function, that I'd have a y-intercept at 0, 10. So using all this information and using the fact that we know that it's concave down on the left-hand side of 1, and we know it's concave up on the right-hand side of 1, we can use that information and go ahead and graph. So, and the point of inflection is the point where our graph changes. So what we're going to have here, our point now is changing, and now we have concave up. So this is what our function will look like. Make sure that we label y equals x cubed minus 3x squared minus 9x plus 10. So our next example, we want to sketch a graph of y equals x to the power of 4 minus 2x cubed. So first step, we need to find our first and second derivatives. So this will be equal to 4x cubed minus 6x squared. We'll set this equal to 0, factor out a 2x squared, pardon me. And what we'll be left with is 2x minus 3. So we have x equals 0 and x equals 3/2. These are our critical points. And the values at our critical points, when we sub in 0 into our function, at the beginning here you get 0. And if you sub in 3/2, you're going to get -1.6875. So these are our critical points that we know already. Now looking at our second derivative, this will be equal to 12x squared minus 12x. Set this equal to 0, factor out a 12x, and what you'll be left with is x minus 1. So we have x equals 0 and x equals 1. So we're going to use those values, and we're going to look at our second derivative and look to see if our function is going to be concave up or down. So set up our chart, f double prime of x, and our function, and we're going to look at 0 and at 1. So on the left hand side of 0, so if we were to take negative 0.1 for instance, and we sub it in to our derivative here, what we're going to get is a positive. And if it's positive, we know our function is going to be concave up. Now if we take a value between 0 and +1, say 1/2, and sub it in here, we're going to get that it's negative. So this would be concave down. And then if we sub in, say, a point 1.1 into our function, our second derivative function here, we're going to get that the second derivative is positive, and therefore it would be concave up. So x equals 0 and x equals 1 are points of inflection. So let's just look at those 2 points here. So looking at f of 0, which is equal to 0, we know that our function is going to be concave up when x is less than 0, and concave down when x is greater than 0. And looking at when f at positive 1 is equal to negative 1, our function is going to be concave down when x is less than 1, and concave up when x is greater than 1. So we also want to look at our critical points. So at x equals 0, since we know at x equals 0, it changes from being concave up to concave down, and this is supposed to be a critical point. We know actually what's happening here is that it's neither a max or min. And when we look at our other critical point of 3/2, and we know the point there is 3/2 negative 1.6875, we know that this therefore is going to be a local min. Because x is 3/2, it's greater than 1, and we know our function is concave up, giving us a minimum value. So now, using all this information, we can go ahead and graph. So now we're going to graph our function. So we know our point 0, 0. At this point, we know that it's neither a max or min. And we know on the left-hand side is going to be concave up, on the right-hand side is going to be concave down. So it's that point where it changes direction. We also know that we have a local min at 1.5, negative 1.6875. So this value would be about here. And we also know that we have the point 1, negative 1. And at that point 1, negative 1, we know that the function is going from concave down to concave up. So what our function is going to look like, it's going to look something similar to this. Remember, this is a sketch, but do make sure that you label your important points and make sure that it shows concave up and concave down. Now in example 3, we want to sketch a graph of f at x equals x to the power of a third. So this one is actually a very unique case, so let's look at it. First step is we want to find our first derivative. And when we do that, we are going to get a third x to the power of negative 2/3. So I can rearrange this and set it equal to 0. So it will be 1 over 3x to the power of 2/3. So what you notice here is that x equals 0 is a critical number. However, at x equals 0, what's going to happen is we are going to have a vertical tangent. Okay, because if I subbed in 0 here, that's going to make the whole function not exist. So I know that it's going to actually be a vertical tangent here. Still, we need to look at our second derivative, and what we'll get is negative 2/9 x to the power of negative 5/3. Rearrange, set it equal to 0, so we have negative 2 over 9x to the power of 5/3. We know this doesn't exist. So now in this case, we're going to look at whether the function's increasing or decreasing and whether it's concave up or concave down. So when we're talking about increasing or decreasing, we're talking about looking at our first derivative. And we'll look at it on either side of 0. So on the left-hand side of 0, if you were to take the point, say, negative 0.1, you're going to get that your function is positive, and therefore the whole function is going to be increasing. And if you looked on the right-hand side of 0, say if you looked at 0.1, then you would have it also increasing. So now let's look at our second derivative to figure out if our function is concave up or down around our critical point of 0. If we subbed in 0 here, we would get that our function would be positive. A number on the left-hand side of 0. We would get that our function is positive. Therefore, we know that it would be concave up. And if we were to look on the right-hand side of 0, what we're going to get is that our function is actually going to be negative, and therefore our function would be concave down. So when talking about this, if we want to look at the fact of the limit as x approaches 0 of our first derivative, so therefore that's looking at the limit as x approaches 0 of 1 over 3x to the power of 2/3. This is actually showing us that it's going to be approaching positive infinity for the whole function. So now we can go ahead and sketch this graph. So I know that I have my point 0, 0, because if I subbed in the 0 for my x into my function, I'd have that point there. And there we know that looking on either side, we know our function is going to be increasing. However, we know our function on the left-hand side of 0 is going to be concave up. And on the right-hand side is going to be concave down. Another thing that we do know is that our function actually has a vertical tangent at x equals 0. So knowing that it has a vertical tangent at x equals 0, we know that our function is going to be almost a straight line at 0. So what we're going to get is that our function will look something similar to this sketch below. Make sure that we label f at x equals x to the power of a cube.